Hello everyone. In this presentation, we will be talking about the tech stewardship behavior analysis of our project PV Grid Control. Our group consists of 5 electrical engineering students: Michaela Chislett, Monica Hunter, Kennedy Menchington, Charity Talbot, and Sydney Walsh. For today's presentation, we will look at the idea of technological stewardship in general. Then we will review a technical overview of our design project. Next, 3 technological stewardship behaviors that relate to our capstone will be discussed. These include take responsibility, widen approaches, and seek regeneration. Finally, the team's reflections will be reviewed. Before getting into the objective and problem behind our design and how tech stewardship connects to it, it's important to first understand what tech stewardship is. For our group, technological stewardship introduces ways to apply behaviors in order to help promote technological innovation. While doing so, it aims to ensure that there is a benefit for all society while still realizing the possible unintended consequences. These behaviors and ways of thinking work to ensure that designs are equitable, inclusive, and sustainable throughout a project's lifetime. When applying tech stewardship practice, innovators are forced to reflect on the societal impacts in their actions and work on how their technological choices will have both positive and negative effects. So now that we have an idea of what tech stewardship is, Charity will discuss our design.
Current grid-connected photovoltaic or solar arrays on the market have a reduced performance as the power demand varies constantly and the grid becomes unstable, creating unwanted disturbances. These disturbances result in inefficiencies that reduce the overall power supplied by the solar panels. Our design, PV Grid Control, focuses on grid-connected solar panels or PV systems which improve performance. The design uses a customized high-efficiency control system that eliminates disturbances and optimizes power output through a low-cost and reliable design that is an accessible option for an average homeowner. The team set out multiple intentions to follow and meet throughout the design process. These intentions have been separated into team-based intentions and design solution intentions. Intentions highlighted for the team include ensuring that all team members learn and grow from one another, having equal contributions to the design with each member realizing their strengths and weaknesses. Our design solution intentions include creating a user-friendly solution that is accessible to everyone, design that has the ability to adapt with the advancement of technology. When working with the team, it is important to identify a set of values that the team shares to incorporate in the design. The values we chose to prioritize for PV grid control are affordability, reliability, evolution of green energy, and to embrace mistakes, being aware that mistakes are bound to happen and having the ability to learn from them. When starting the design process, a number of intended effects or objectives were outlined for the team to follow. These effects were a high-efficiency power output that eliminates disturbances, a product that meets power demand and allows users to reduce their reliability on the grid, a clean design that doesn't include unnecessary technology and convoluted ideas so the average user can take advantage of the product, a long-lasting and environmentally friendly design that doesn't require component replacement over a short period. As with all design projects, along with the intended effects, there were also unintended consequences that occurred. First, the design was of no interest to local power companies as renewable energy sources within utilities are not involved in Newfoundland at this time. Finally, solar panels and their required control systems constrain hazardous heavy metals and materials that lack proper recycling and disposal options, causing negative effects to the environment. After a clear understanding of the technical aspects behind the design, the team has chosen 3 technological stewardship behaviors to connect our design to. Sydney will now begin the discussion on take responsibility.
The first tech stewardship behavior that the group takes into consideration is take responsibility, since this behavior relates to the safety, environment, and impact the design will have throughout its lifetime. By learning to take responsibility, we can understand the potential impacts the design may have, admit to our failures, and adjust the design as needed. As this design is a grid-connected system, it was important to realize any relevant electrical utility standards and engineering practices, Ignoring these standards could result in unintended effects on the grid, causing large-scale effects on the local power system. Looking into challenges we faced, an unintended tension arose from over-engineering and overthinking problems that could lead to the detriment of the design. Although we have worked well on realizing our mistakes and failures, and we have been able to find solutions, oftentimes the team would overcomplicate the problem and look for a convoluted solution. From this tension, we were able to ensure functionality and performance and look for a clear solution rather than overcomplicating. A polarity map helps us to identify the strengths and weaknesses associated with this tech stewardship behavior. A positive outcome of focusing on tech development would be the innovation of a functional and efficient control system that makes green energy available for all. However, if we only focus on tech development, our design could become over-engineered and lose its target audience of the average homeowner. A benefit of tech stewardship is that our solution will appropriately address the specific problem we set out to solve, which is control of a residential PV system. If we only focus on tech stewardship, we may become overwhelmed with the problem in the green energy sector and try to solve too many at once in our design. It is therefore important to have a blend of tech stewardship and development in our design to ensure that it is functional and efficient, but also addresses the problem associated with the current solar control systems.
Seeking regeneration is the enhancement of the health of systems that the design is interacting with. The design seeks to enhance the accessibility and efficiency of small-scale PV systems. It will increase the ease at which people are able to install small-scale PV systems in their residences, both financially and by decreasing the technological knowledge required of the individual user. An increase in the use of residential PV systems will proportionately increase electric grid stability, especially during periods of high demand on the system. By introducing these new means of power generation for the average user, the demand for power generation from fossil fuel-based generating facilities can be decreased. Unfortunately, solar panels are manufactured using fossil fuels and toxic metals, and therefore the increase in demand for solar panels will increase the use of these materials. Going forward, the team would like to explore encouraging the use of life-extending maintenance practices for anyone that uses solar panels. The following polarity map shows the tension encountered between technological development and stewardship while seeking regeneration. Seeking regeneration through a tech development lens will allow our design to be an accessible green energy control option that promotes use of PV systems for homeowners. A focus on tech development may cause us to indirectly promote the consumption of energy and/or unstable materials, such as those found in the solar panels themselves. A tech stewardship approach will allow us to ensure our design contributes to the availability of sustainable energy and uses components with long life cycles. However, it is important to consider how a focus on sustainable components may limit progression and functionality of the design, which would have greater environmental benefits than the components themselves. It is therefore important in our design to both offer accessibility to renewable energy systems as well as enhance the sustainable energy alternatives.
Throughout the design process, the group sought to widen our approaches through the exploration of different alternative solutions that may have contributed in completing the project. This included the consultation of outside parties such as Newfoundland Power and extensive literature review. During this time, we also remained open to changes in the original design that would help to improve the overall innovation and efficiency of the project. However, this way of thinking also developed the unintended tension of straying away from the original problem in an attempt to be more innovative. Going forward, the group is committed to identifying specific project goals while remaining open to new strategies for achieving them. The following polarity map shows the tensions encountered between technological development and stewardship while widening approaches. Widening approaches in tech development will allow us to draw ideas from existing similar technologies without plagiarizing. However, if we ignore technological stewardship, we will end up prioritizing control methods that are not the most effective for this application. By applying tech stewardship thinking, the design can incorporate new control methods that have been thoroughly tested and determined to be the most effective for this project. However, this could also lead to incorporating too many new ideas and losing a clear objective. It is therefore important to ensure that we are incorporating new ideas but still considering existing technology that has been successful to make the best design possible.
Upon reviewing the tech stewardship behaviors and how they apply to our design, we have been able to realize that there are no correct answers to the tensions that can arise. When starting the project, the team was confident in the design and were not aware of the gaps and areas for improvement. More specifically, the negative impacts of the design were not considered to a high enough level. These include areas of sustainability and life cycle, especially at the end of life disposal, as well as straying from the problem we were looking at in order to create a final prototype and over-engineering when a problem occurred. When considering the most challenging behavior, take responsibility really stands out. In the design process, whenever a problem occurred, we would often overthink a solution. This caused frustration and could have easily caused the design to fail, as it was often really hard to rebound. Overall, however, taking the tech stewardship behaviors and values into consideration, we were able to minimize these effects and take corrective action for the remainder of the design process. The findings of these tech stewardship behaviors and values will be useful going forward in our careers as we shape into professional engineers. Here we have a little list of our references, and thank you everybody for listening.